Okay, I'm recording. And I'll share. Okay. And we'll probably give everyone just a moment. So I'm gonna go get
Sure.
a bottle of water and we'll be back. I'll be back in just a moment to see if anyone else shows.
Lauren, are you also in semester system?
Yeah, I'm on the semester system. Are you on the quarter system?
No, I'm in a semester system as well, but then we only get one break in the fall semester, which is just like a week-long Thanksgiving break.
Oh man.
I know it's terrible because like after Labor Day, we don't get any holidays off until um until Thanksgiving.
That's a marathon. Like, because right around now, like I'm so burnt out. It happens every year, no matter what I do. It's like I don't want to come to work.
Exactly. Or sometimes, I mean, I think we do get Veterans Day off, but then sometimes Veterans Day falls on a Friday, and we don't offer class on Fridays anyway. So
So
it's
it's
kind of
like a wasted holiday.
yeah, exactly.
Where are you based again?
I'm in San Diego.
Okay,
Yeah,
that sounds nice.
it is. It is.
Besides the fall break situation.
The first time I've ever heard about that, actually.
Hmm. Now, where did you go to school beforehand?
Prior to this, I was at UC Irvine in Orange County, but that was a quarter system.
Okay. Okay. Yeah, when I was in grad school, we did the quarter system, and yeah, I don't think we had a fall break. So yeah, good point. Oh, good. Us delaying a little bit. Art is here, so it was worth waiting a little bit. Hey, Art, how you doing?
Doing great, doing great. Good to see you.
Good to see you. Okay, let's jump in. Let's see. Last time, what did we do? We finished Lab 3. That was the Kepler third component of Lab 3. And we put in the observations for Lab 5. So at the beginning of Lab 4, we opened up Lab 4, and kind of the first thing you see are the overview videos. You can design a pre-lab talk around those overview videos. And then before the students get to work, you have them put in observations for upcoming labs. The upcoming lab is Lab 5. And so we went over those observations. And those observations, like Lab 4, the instructor puts in the Lab 5 observations. In Lab 4, it's because it's a tricky observation. Parallax, getting uh, telescopes in both hemispheres to image simultaneously requires target of opportunity access, et cetera, and sometimes multiple attempts if there's bad weather. So we have the instructor do that. And with Lab 5, the reason's different. It's a pretty simple observation. You're observing an Aurelian star in a globular cluster once an hour, 50 observations. And it's just a big, bulky observation. It takes a lot of credits, and students don't have that many credits. So the instructor puts that in and shares it. And so we went over that last time. Okay, let's see here. Okay, so here we are in Lab 4. Here are the overview observations. Here's the observing guide. I guess I'll just open that real quick. But yeah, this is what we did last time. We have the observation planner. So you look at Lab 5 and it says put the observations in 2 weeks before the due date, probably 1 week before they're doing the lab. And then all the information about putting that in. Okay. Review sources of error in previous lab, etc. Okay. Goals. Goals for Lab 4. So we're into the cosmic distance ladder, and kind of the lower rungs of the cosmic distance ladder is parallax. And so we do this in kind of 4 components. We do very nearby. So we have this manual exercise. Some institutions skip it. It depends on whether you have a good place to do it or not. But I find it's a good thing to do. Otherwise, with the astronomical ones, they're looking at images on their computer, taken from different locations on Earth. There's a small shift, but they may not really understand the geometry of what's going on. So it helps to do the manual exercise. If you have a place, if you can squeeze it in. Then we have 3 astronomical observations. One is the main belt asteroid, which you put the observations in a couple of weeks ago. With one set taken from the north and one set taken from the south. And they learned how to do that analysis. Here, got the mute, great. They learned how to do that analysis in Afterglow, measure the angular shift, and calculate the distance to it. And then we do 2 more. So there's some repetition here. There's the manual exercise, which is very different because it's 3-dimensional. And then there's repetition with the astronomical exercises. And I think it's the good kind of repetition, the reinforcing kind of repetition. So it's very similar. Each one has a little twist. And including the manual component, it can be kind of a lengthy lab. When we do it, our manual component's on the roof of the building, so the students don't have to go far. But still, it eats up time to do that manual component. And when they come back down to do the astronomical components, they normally only have time to do 2 of the 3. But because it's repetitive, they then know how to do it, and they can do the last part at home if they don't get it done. But the 3 parts are the main belt asteroid, and then they do Venus, and that one's archival for reasons that you'll see, having to do with it being such a bright source. The observations have to be a little specialized. And they're doing Venus to measure the astronomical unit, to determine how many kilometers are in an astronomical unit. The whole point of the cosmic distance ladder, and the course is built around the cosmic distance ladder, the whole point is to go farther and farther and farther out. And so you have to keep calibrating things as you go. And so we use Venus, observe it at a particular part. It's in a particular phase, so it's at a particular place in its orbit, which means it's a certain number of 1.34 AU away in this particular case. And they figure out how many kilometers are in an AU. And then once they've done that, they could do stellar parallax. Of course, they could do stellar parallax without calibrating the AU. Stellar parallax is, of course, when you're on opposite sides of Earth's orbit instead of opposite sides of Earth. But kind of the pedagogical sequence is, they learn how to do parallax from opposite sides of Earth, measure distance in kilometers, and then they, with the Venus data, they're going to calibrate the AU in kilometers. And so then it makes sense. We can go out to farther scales. It's a calibrated scale. Okay. And then we do a stellar parallax. And that's also archival data for the same bright source reason that you'll see. Equipment. For the manual component, if you do it, going to reuse the protractor and string that if you did the globe version of Lab 2, this is how we measured the sun angle above the horizon. We put it up on the globe and measure that angle, so we get to reuse this. And most people do the Stellarium version of Lab 2, so you may not have used these yet. They're really inexpensive. Just get a box, but make sure you get the ones with the little hole at the 0, place so you can tie the string in. That makes it easier. Otherwise, you're trying to drill holes or tying it some weird way. It gives you inaccurate measurements. So that, some distance measuring thing like a tape measure or a meter stick or yardstick. I think we do this in feet. We'll see in a second. And then, of course, computer and internet for the astronomical parts. Okay, 2 background sections. The first is setting up the cosmic distance ladder in general. We're about to do a bunch of labs on the cosmic distance ladder. So I just start with a kind of the basic observation. This is one of my favorite sentences in introductory astronomy. You cannot see distance. And here we have the picture of the weird disembodied head that my textbook likes to use. looking up at a field of stars, see stars A and B, they look the same brightness, but that does not mean they're the same distance. Or if something is brighter, doesn't mean it's closer. Could just mean it's more luminous. So we can't see distance. So astronomers have built up a bag of tricks that build upon itself. We use one trick to get out to a certain distance, and then there's another trick farther out, but we first have to calibrate it using the first trick, calibrate it, can use the second trick, then we use that to calibrate the next trick, and so forth. And we bootstrap our way out. And here you can see what parts of the cosmic distance ladder we're going to do in this course. So this is a preview of stuff to come. Of course, the cosmic distance ladder has many, many different things in it. This is a simplified, boiled down version because there's only so much you can do in a survey level course, given time constraints and background. But here you can see at the base in lab 2, we ended with that measurement of Earth's diameter. And so that's our starting point. Here in lab 4, we're going to start with Earth baseline. Well, we're going to start with the manual exercise. But after that, Earth baseline parallax. So we use that measurement of Earth's diameter to measure distances within the solar system. This can be done out to about 500 AU, but in reality, with our technology, our telescopes under the atmosphere, we can do it out to like Jupiter, Saturn, if you're really good. But certainly encompassing the main belt. Actually, it's kind of a fun thing. We don't do it in the sequence, but we just did Kepler's third, and we had to look up the distance to Jupiter, to Saturn. And you could actually, if you have more advanced student who wants a challenge, they could measure the distance to Jupiter with parallax, and then do the rest of the Kepler third activity instead of looking up the distance in stellarium. But anyway, once we have Earth baseline parallax and we calibrate the AU, we can do stellar parallax from opposite sides of Earth's orbit. That gets us out to, with us, we just do Alpha Centauri, but with better instruments such as Gaia, you can get kind of halfway across the Milky Way. And then in lab 5, we go farther out. We start with our Lyris. Now, these are no longer parallax. This is standard candles or standardizable candles in some cases. But with our Lyris, we can get to completely across the Milky Way. We use them in globular clusters, etc. Cepheids, we can get to nearby galaxies, and type 1a, we can get to farther out galaxies. And then we have a few other, labs not on the cosmic distance ladder, but while we're out at, well, lab 6 is an application lab of our Lyris and Cepheids. And then lab 7, while we're out on Milky Way scales, we do the rotation curve of the Milky Way. But then we hop back in with lab 8, where we do Hubble's law. That one's actually not a Skynet lab. And now we have a lab 9 where they measure Hubble's constant. Anyway, preview of things to come. And then a background section on parallax in particular. And we'll just start with the simple finger exercise. I tell the students to grab a finger, preferably their own. A little joke, feel free to use it. Sometimes they laugh, sometimes they wince. And, the thing you always do, hold it in front of your face, close one eye, see what it's covering on the wall in front of you, then switch the other eye. There's a large angular shift. Now take your finger and move it out to a longer distance and do it again, shifting your eyes. It's a smaller shift. And I tell them to cut their hand off and move it farther out, and it's a smaller shift. And so if you know the distance between the two observing points, in this case, the distance between the two eyeballs, and you can measure that angular shift, you can calculate the distance to the finger, and hence we could do the same thing to anything else. So again, here are the two cases we do in this lab. Earth baseline parallax, where we have telescopes on opposite sides of Earth. This figure is rather poorly demonstrating the moon. The moon's not in a polar orbit, but you get the idea. The moon actually shifts about 4 moons. It's 3.8 moons if you image it simultaneously from opposite sides, which is quite surprising. Of course, that's hard to see because if you take a picture of the moon, it's a short exposure. You don't have any background stars for comparison. But it's in my lecture course, I assign this as a calculation, and it's kind of surprising. But of course, we're going to be doing things farther out, so the typical shifts are arc seconds, a few arc seconds. And then the other use case here, stellar parallax. Instead of being on opposite sides of Earth, we're on opposite sides of Earth's orbit, looking at a nearby star compared to faraway stars, and you get shifts. And in the case of Alpha Centauri, it's about an arc second or so, and much less for other stars farther out. And here's that geometry again. We saw this in lab 2, where they're measuring the size of the Earth. We saw it in lab 3, flipped around to measure the, we're converting the angular semi-major axis of a moon's orbit around a gas giant into a physical quantity. It's the same geometry. And we'll see it again in lab 6, where we're going to measure the angular sizes of spiral nebulae, as they used to be called, or galaxies. And so we keep reinforcing this geometry here. I need to alter the figure. Some of the educators point out this arrow with 360 should actually terminate here with 360 on the outside. It causes a little bit of confusion. Some people think, I mean, this is 360. So, and next time this one comes up for editing, I'll tweak the figure a little bit. But anyway, angular shift as a fraction of 360 is equal to the baseline between the two observing points divided by the circumference of this big circle, whether it's Earth baseline parallax or Earth orbit baseline parallax, stellar parallax. So baseline over circumference is angle over 360, and the circumference of the big circle is 2 pi times the radius, and the radius is the distance from us to the object that we're looking at. And so solving for distance, we get distance is equal to our observing baseline. Oh, there's the, all that text is new. That's cool. It's equal to the baseline divided by 2 pi times 360 divided by the angular shift in degrees. And they just have to remember to convert from the arc seconds. Well, with the manual exercise, with the protractor, it will be in degrees, but for the astronomical ones, it'll be in arc seconds, so they'll have to convert that. I like reusing these pedagogical concepts, but also, the practical skills in Afterglow. We'll see some use of skills they picked up in lab 1 in this lab. Okay. That's all the background stuff. So now the procedure. And first with the manual part. Again, some people don't do it, lack of time or lack of a place. Though, although the pictures here are for Chapel Hill, I've written it such that you can do this anywhere. And we also do it with online students during the summer, and they find their own locations. And some of them will just do it in their apartment, or you could do it in the lab room if you don't have a good setup. You could, if you have a long table or something, you can use that and put objects like half the way from that to the other side of the room and all the way on the other side of the room. On the top of our building, we have this long observing deck, south facing, and the students measure the distance to the smokestack on this building across the quad, and then farther away, the water tower. Okay. And, this is how you do it. You line up the protractor flush against the wall. The wall really has to be straight for this, particularly if your object's far away. These are angular shifts of only like a degree or so. And so you have to be able to make the protractor flush to better than that. And the instructions say, once you have it there, you get your eyes down to protractor level, orient the string to your target, and then, lift up and read it off the protractor. At the very top, it's, well, it doesn't really matter, right? Yeah, it's 90. So, they'll measure some in the high 80s and some in the low 90s, for something that's far away and it's only a few degrees of parallax. So first angle, second angle, the shift, and then they need to know the distance between the observing points. And I take up a bunch of meter sticks. I take up some tape measures that go out to 25 feet. This observing deck's about 100 feet across. So often their observing points are like 90 feet across, away from each other. And I just let them figure out. Some people will do the is this in feet? Yeah, it's in feet. So yardstick. They'll do the yardstick over and over and over. Some people will do the 20, stretch out the 25 feet of the tape measure and then shift it. The smart students measure the pavers. They're 2-foot pavers up there, and then just count the pavers. I usually don't tell them what to do and let them figure it out. And then they calculate the distance to their object. And the smokestack's 650 feet away, but if you're at another institution or online, well, if you're another institution, the instructor will provide the distance to your target. I just use Google Maps. Once I find a place, I use Google Maps to figure out the distance. And so you'll provide that, and they'll stick it here as the true value. Or if they're online working on their own, they'll use the tape measure to, they do a smaller setup. And so they can actually check with the tape measure the distance away. And they calculate a percent error. And then they go back and do it again for the more distant object. And here's just a compact version of what we went through. Sources of error. I came up with 6 things. If they get 3 of them, I'm happy. Difficulty positioning the string. Now, technically, if they position the string incorrectly, but they do it incorrectly the exact same way for both points, that's not a source of error. I don't expect them to be that subtle. But difficulty positioning the string, difficulty having the protractor flush up against the wall. That's also one, if they did it wrong in the same way at both points, it would cancel out. But precision of the protractor, it's only good to degree. So they should only be able to measure to like a fraction, a few tenths of a degree. So that's, and there's some questions specifically about that coming up. And uncertainty in the distance measurement between the 2 observing points, depending upon their technique. And then 2 that they never get, but I have them here. If the objects are not exactly perpendicular to your observing baseline, then there's some more advanced trig that we're not introducing here. And also, if the object's not sufficiently far away, or another way to view that, if the parallactic angle is large, like 20, 30 degrees or more, then the small angle approximation breaks down. And so it's not a triangle, but a chord. And so there'll be one you overestimate, one you underestimate. For the main belt asteroid, we're just trying to get in the ballpark, something times 10 to the 8 kilometers. So, we're not trying to be super precise. All right, some questions here. Which was less accurate? And it could have been either, but which should have been less accurate? And the one that's farther away should have been less accurate. And why? It's because it's approaching the limit of the angle measuring device. If your shift is only half a degree and your angle measuring device is only good to half a degree, then you're going to, have greater inaccuracy. For a fixed baseline, at what point does parallax cease to be an accurate technique? And I say, do not say 10 kiloparsecs, because up in that inverted pyramid, it said you could do stellar parallax out to 10 kiloparsecs. And I know students just started writing 10 kiloparsecs. What we're looking for here is the limit for a fixed baseline is when you reach the inaccuracy of your device, of your angle measuring device. So kind of related to the question up here. And then what are 2 ways you could do better? One is you can have a device that's more precise in measuring angles, like maybe use professional surveying equipment instead of this protractor with the string. Or in space, use Gaia instead of Skynet telescopes in the ground. That's one way. The other way is to have a bigger baseline. And that also ties into why we go from Earth baseline parallax to stellar parallax with the Earth orbit as the baseline. Okay, so that's the manual component. And I think you all see the value in it, in actually physically doing it. They can actually see, 2 different observing points. I'm here, now I walked over here. I see the triangle, I see the geometry. Once you get to the astronomical stuff, it's just images on the screen. So that all gets a little bit abstracted. And also we put in these kind of teaching questions in this section. So hopefully you find a way to do it. Okay, here's the observation of the main belt asteroid. We went through this a couple weeks ago. Hopefully you got data. I did it once with you, once with my TAs, and data came back on the first try for both. So that doesn't always happen, but it was very collectible this semester anyway. Next, we're going to identify the asteroid. Okay. And here there are a couple ways to do this, but we're going to use the way that they learned in lab 1 using the DSS. So let's go to Afterglow here. And let's, Davida, I don't know the pronunciation. Let me actually go to Skynet for a second here. So here it is a prompt USASC. The first one was at 083043. Let me back up. And then here's my prompt 6 in the south at 083040. So these two, they're within 3 seconds of each other. And that's what you want. You want to find an observation in each. They're very close together. There may be some other ones in here that got even closer, but 3 seconds is pretty close. They're 40-second exposures, so at worst, they'll be 20 seconds separated. And asteroids do move noticeably, measurably over these periods of time. So getting it within 3 seconds is important. So I'll use those. I loaded and so it just happened that the first one in each observation was very close in time. That doesn't always happen. Sometimes one slews into position and starts observing. The other one's has a longer way to go and gets there 20, 30 seconds later. But in this case, let me back up. The first one in each was pretty synchronous. So I'm going to open prompt 6 one here. Okay, so over here I have sync orientations on. That's why they're flipping around like that. It'll be off initially. Let me reset these orientations. So it's like what you get initially. Okay, so here's one of the fields. Here's the other field. And at first glance, it's not necessarily clear the alignment. But then if you come over here to the gear sign and turn on sync orientations, as long as both images have a WCS, if I move my mouse around, if I have coordinates down here, then everything else will sync to whatever image you were on when you clicked that. If I flip between them, you can see the stars now are lined up. And of course, there's that brighter thing near the middle. It's almost certainly the asteroid, unless we had a huge pointing problem. And that's just a ghost of Jupiter. We can ignore it. Okay. How do we determine which one is the asteroid? Again, most likely it's the central one, but you can just come back over here to the gear and import the DSS. And it should also be lined up. So yeah, the stars lined up nicely. And there's clearly something in our image that's not in the DSS. So I'll split these. I guess I'll split to the right. And they go through the same process, I believe, of marking things, common things in each image. Like they did when they did their, oops, I missed. So those three, these three, this one. I think when I have, my space is a little cramped right now. Let's close this out. Okay. When I was hovering my mouse over it and numbers popped in, it caused it to rescale. And so I keep missing, keeps moving when I'm trying to click on it. I mean, you don't have to do all these, but enough. And then it's clear this is the thing that's not in the other one. And let's see, where are the I gotta click on it, and I'll label this as the asteroid. Okay. So there are their two images that they're gonna upload here. Okay. Now, now that they've identified which one's the asteroid, we're going to measure the parallax. Okay, so let's come back here. To measure the parallax, what we're going to do is we're going to stack these images. So it's a two-step process. First, we align them. That's the third from bottom, the aligner. Let's select these two images, not the DSS, but the two images that we took simultaneously. Make sure crop, rotation, and scale at least are on. Since they're different telescopes, the cameras do have different scales. With same telescope observations, you just need to crop and rotate, but different telescopes, you also have to make sure scale is on. We're going to use the WCS. There are other ways to do alignments, but we'll use the WCS to align. And I got to pick a reference image. Either is fine. Submit. Okay, get rid of this WCS here. So here's one. Here's the, I had to reload it because it's been aligned and cropped. Actually, just flip in between them. I can see the asteroid shifting. And it's not motion through time. That's parallactic shift because these were simultaneous. It's really kind of cool if you think about it. Okay, and then we're going to stack them. Let's just make the measurement easier. Select these two. Propagate mask will maintain the cropping, but everything else can be the default settings. We don't need to do anything fancy. And so they're stacked. It'll make a new file that it starts out with whatever characters the two files had in common and ends with _stack. So this is the stack of the two. And you may have to tweak the saturation level, the brightness and contrast to see the separation. See, you can see it there now. You go to the plotting tool. And although there are centroid clicks, sometimes it's kind of messy. Sometimes they overlap. And so I just forget the centroid clicks and do it manually. And I got a 6.4 arc second separation here. Observe simultaneously. That's due to being on different parts of the planet. Okay. Pretty cool that you can do this, I think. It takes a global network of telescopes to do this lab, at least with data you collect yourself. So we come back here, they load up their, they'll frame this up and do the screenshot and then send that up into the lab. Then they do the calculation. What is the angular shift in arc seconds? What observatory in the north did you use? We use the second one here is Moorhead, so it's 0.55 Earth diameters from Ceratololo. So we record that fraction. And then I ask them, what diameter did you measure for Earth in lab 2? We're not going to use that. I then ask them, what's the true value? But this is just to remind them that these labs are building on each other. They are bootstrapping. We're not going to use our previous measured value to calculate distances because the errors will add up and they'll accumulate as we go through the distance ladder. But I do remind them, hey, you measured Earth's diameter here, and then we get the true value, and we take the true value multiplied by the 0.55. That's our baseline. And again, here's the equation from the background section. We have the baseline, we have the angular shift, which they'll have to convert from arc seconds to degrees, and they calculate the distance. And main belt asteroids are between 1.6 and 6.4 times 10 to the 8 kilometers away. So we ask, is your measurement reasonable? It should be in this range, unless for whatever reason you imaged like Neo or something. I don't think any of that. On that Wikipedia page where we pick our asteroids, I think they're all main belt asteroids. Sources of error. How well you selected the center of the asteroid in each image. And how close were they in time? because if there is, the more seconds that are between them, the more of a shift you can have due to motion of one with respect to the other. And then also, no one gets this, so there are 3 points. There are 2 points for 3 possible answers, and the third one is the baseline between the 2 observatories is probably not exactly perpendicular to the asteroid. The asteroid is in the main belt, and if Earth were straight up and down, they would be perpendicular, but Earth's tipped 23.5 degrees. Though if we're in this orientation, the projection's perpendicular. You can't tell I'm doing it at this point, but if our tilt is perpendicular to the line of sight, then it does work. But if it's along the line of sight, then that's a source of error. No one ever figures out those geometric ones, but it's there anyway. Okay, now let's repeat this twice with little twists. With Venus and then stellar parallax with Alpha Centauri. So Venus. Okay. So we set it up here. The goal here is not to measure the distance to Venus. I mean, we've measured the distance to something, and they get that. We're, again, using Venus to calibrate the AU. And here's a little, call back to Kepler's third in the previous lab. With Venus, we measure its orbital period as 0.62. That implies by Kepler's third that it's 0.73 AU from the sun. So here's a little diagram. We're 1 AU by definition. It's 0.73. And often in my lecture classes, I assign the problem. That means the difference is 0.27. And so, if we do Earth baseline parallax when at closest approach, what is the distance, how many kilometers? So, Earth is so many kilometers across. We do Earth baseline parallax to Venus at closest approach. So whatever that is in kilometers is 0.27 AU, divide by 0.27, and the number of AU and number of kilometers in an AU. So that's what I assign in my lecture classes. But in reality, you can't do that because the sun is right there in the sky. You can't do an Earth baseline parallax measurement to Venus in that configuration because Venus is right by the sun. You can't see it. So it's nice and simple for a lecture class, but here in the lab, got to be a little bit more creative. So you have to do it at some other position in the orbit. And so we're going to do it in this position when it's in this phase. When it's in this phase, that gibbous phase, that means it's right here in the orbit. And I've pre-calculated it's 1.34 AU away. So we're using archival data. And in this archival data, Venus is 1.34 AU away. We measure the distance with Earth baseline parallax in kilometers, and then we know how many kilometers are in AU. Here's the tricky thing. I'll just go over to Afterglow and load these images in. Files, sample, 101, parallax, Venus. Okay, simultaneous images from Prompt and Moorhead. Again, Moorhead's in Chapel Hill. So I loaded them in and they look weird. What's this big black? And we already have the alignment turned on. So if I hop between these, the stars, see the stars are in alignment. So what is this big black circle? And I think I may have mentioned this at the end last time. Venus is really bright. And so if you don't want to saturate Venus, you have to do short exposures. But if you do short exposures, you don't detect any background stars. It's the same thing like pictures of astronauts on the moon. The conspiracy theorists, where are the stars? Well, it had to be a short exposure or you'd totally wash out the astronauts in all that bright sunlight. So to get the background stars, you have to image longer, but then you totally saturate Venus and can't make a precision measurement. So this is what we tell the students in the lab. It's a lie. And so if you're more ethical than I am, feel free to fess up. But I say we had these special custom filters made, central neutral density. So they're regular high throughput filters in the outskirts, but they block like 99 point something % of the light in the middle. And we put these on telescopes in the north and the south. I can't keep, even if I were to pay the money to do it, I can't keep them on those scopes because the filter spaces are precious. People have other filters they want to use for other things. This would only be used for one thing. So the data would have to be archival anyway. So in the lab, I say we did this, and here's the archival data. In reality, I just assigned my postdoc to doctor it, and he did a really good job. Aaron Lacluse goes by Clues. He's not my postdoc anymore. He's professor at Central Michigan. But it's funny because Clues is the most ethical person on the face of the planet. Like when we're in Chapel Hill observing late at night, we go out for a bite in the middle of the night. The streets are completely empty. He will stand at the crosswalk until the walk signal turns on. He will not walk into the street. He's that ethical. I don't know how I convinced him to do this, but he did it. And we do this with the Alpha Centauri data as well. So anyway, let's just do it. It's, we have enough background stars that we have a WCS, so it's the same process. You start by aligning, clear out the asteroid, select the two Venus observations, pick one as the reference, make sure enable scale is on since they're different telescopes, submit. So we'll align them and crop them. Okay. So the stars are stationary. Of course, the central neutral density region's moving, but Venus is also moving too. So to make that measurement, we're going to stack Venus, Venus, propagate mask to keep the same cropping and submit. And here's the Venus stack. And so you can see, right? I don't even have to adjust the brightness and contrast. You can see the parallax there. Can't use centroiding because they overlap, but eyeball the center of one, the center of the other, about 6.4 arc seconds. Okay, going back to the lab, it's going to be similar. They're going to do a screen capture and upload it. Angular shift, fraction of Earth's diameter, using that table from above. This was also Moorhead, so again, it's 0.55. And then they calculate the baseline using the true diameter of Earth, calculate the distance to Venus using that baseline and that angular shift converted to arc seconds. They'll get something, and that something is equal to 1.34 AU right here. But they divide by 1.34 and they know how many kilometers are in an AU. True value is 1.5 times 10 to the 8, so percent error. Sources of error are the same. Difficulty selecting the center of Venus in each image. Possible contamination by motion from if there is a time difference between those two images. I'm not even sure. Let's see. It doesn't say because they were docked. Oh, no, that's the stack. You look at just one here. Under the info, yeah, we don't even have a timestamp because it's old and doctored. But anyway, that's still a source of error if they weren't taken exactly the same. And again, the baseline between the telescopes may not be precisely perpendicular to Venus. They get 2 of the 3, great. Lastly, Alpha Centauri. Okay, so now we're doing stellar parallax. Our baseline is no longer Earth's diameter, but the diameter of Earth's orbit, which is 2 AU, and we just measured how many kilometers are in an AU. So we'll go to Afterglow. We can do this real easy. Back it up, go into the, and of course, here are some backup asteroids in case your asteroid didn't work. But here's Alpha Centauri. There's one. Now, these are not taken simultaneously, one in January, one in July, opposite sides of the orbit. And of course, they weren't taken at all. These are doctored. And actually, there's an internal joke here. The background stars aren't even the right background stars. In the earliest version of Skynet, Skynet 0, if people forgot to enter RA and DEC, it would just image 00 in the sky. So we built up this giant collection of images of right ascension 0, declination 0. So just as an internal joke, that's the background field. And then this is Alpha Centauri A and B. It's a binary. Actually, trinary, there's C, but it doesn't show up here. Okay, so hopping between the two, background stars going to work out. So let's align these. Alpha 1, alpha 2, reference image. These were taken with the same telescope, so I shouldn't have to scale. You can if you want, doesn't really matter. Submit. Then I'm going to stack them. And this one has a little twist because students want to measure the difference between Alpha Centauri A and Alpha Centauri B. And that's not what we want. We want the angular shift of either of them. So here is the new file. Cruise did a really good job. Even the double diffraction spikes and everything match up just as you would expect. So zooming in here, let's adjust the brightness and contrast a little bit so we can see the separation better. Okay, now Alpha Centauri A got a little saturated, so it's maybe not the best. So we tell them in the lab to use B. And they're kind of overlapping, so you kind of have to do it by eye. But what I get here, 1.8 arc seconds, that feels a little high, but maybe. Yeah, 1.8 arc seconds. Okay. So they enter it here. The baseline with stellar parallax, it's always 2 AU, but now they know how many kilometers that corresponds to. So using their measurement and then the true value, they convert it 3 times 10 to the 8 kilometers, calculate the distance to Alpha Centauri in kilometers. Again, we could have them do it in AU, but we're trying to reinforce that these things bootstrap upon each other. And so we have them do it in kilometers. They Google and record the true value to Alpha Centauri in kilometers, calculate percent error. And again, sources of error, difficulty with the centers, maybe the baseline wasn't perpendicular. The only one that's not here now is the timing. We don't take these simultaneously. These are supposed to be 6 months apart. So the precise timing of the Earth baseline parallax is not a source of error. And that's it. So as far as parallax labs go, I like this one. It's hard to collect the data, but once you have it, it's pretty cool. It's not something you can normally do in a class. I remember as a grad student, we did parallax stuff and would set up like fake setups in our room. It often actually the one in grad school we had to do if it's too near, as I said, it's no longer a small angle approximation, and so the correction is actually pretty significant once you get beyond angular shifts of a couple degrees. You can be very off with your distance measurements. But anyway, that's it. Any questions?
Dan, I have a question. When it comes to the alignment stage, when you're having those two images together, specifically for Alpha Centauri,
Yes.
does Afterglow align the two images based off catalog stars?
Yeah, it's using the WCS. So these, we made sure that there's a WCS on them. As long as they're, yeah.
Okay.
But they're
Alpha Centauri. It's like just based off purely from WCS. Got it.
yeah. Of course, these are fake images, so we were careful to make sure it worked out right. But I mean, those are real images of Alpha Centauri and real images of background stars, but then we had to assemble them. And we did it such that the right answer came out. But under the alignment options, you do have other options. WCS is the easiest one. As long as WCS has been added, which Skynet will try to do automatically. And there's even a tab up here, you can improve it. You can do better WCS solutions in Afterglow. But we do have a variety of alignment options. You can select sources manually and align to them. You can select sources automatically. And what's nice about those, so this is more for the astrophotography course. If you're trying to, you have an image, you have background stars, you calculate a WCS, there's going to be some error there. and same with your other images. And then if you align with the WCS, the errors are compiling, right? The stars are a little bit off from the WCS. You match the WCS, which is off from the stars. And so you may not get perfect alignments. And we noticed, particularly if you have a globular cluster with lots of stars, centrally concentrated, you can get errors in your alignment in the corners. And if you're doing like a red, green, blue combination, you get chromatic separation. And so instead of doing, for that kind of scenario, we have, it does a direct image to image. Source extraction extracts the sources and aligns the extracted. It's slower. And then we have ones like feature-based alignment, if you're trying to piece together a lunar mosaic, for example. These have all
On
sorts
that
of,
note, yeah, on that note, if you're aligning by WCS, would
Yeah.
you advise that when we take the simultaneous images, we pick telescopes that have similar pixel scales?
No, it will compensate for that. And by clicking on enable scale, you can just click on them all. You don't really need skew unless your CCD is warped or something. But if you have different telescopes with different pixel scales, if you turn this button on, it will stretch one to match. It's a matrix solution, right? We have a rotation, we have a scale, we have possibility of skew, and it does some kind of linear algebra to find the best solution. Vladimir Kupriyanov is my algorithms guy. He codes all the algorithms in the back end. He's pretty good.
I guess my last question is more pedagogical. In terms of, I guess, illustrating the point that at some distance, parallax is no longer effective. I guess, how do you communicate that to students?
Yeah, that's a little tricky. And again, often they'll just, for those who actually read the background section, which is rare, they'll say, oh, parallax is used out to 10 kiloparsecs, and so that's their answer. But here, at least with those questions, I was trying. If there are better ways to do it, I'm happy to take feedback and revise the questions. But I'm trying to get them to think about the two things that go into it. The measurement of the angle and the baseline. And so your technique is only going to be as accurate as those two things, as your angle measuring device. And you can have everything from this, which is super crude, to Gaia, which is super accurate. And then the other way to do it is to increase the baseline, which speaks directly to the two techniques. But people have a hard time realizing that, okay, ticks are only 1 degree. Best I can measure is probably 1/3 of a degree. And so that is actually what's limiting my ability. Once I'm trying to measure things with 1/3 of a degree angular shift with a device that can only measure accurate to 1/3 of a degree, it's garbage. But these are important things to learn, right? It ties into sources of error. And we're trying to get them to, stop saying human error, measurement error, calculation error. And really what we're looking for in sources of error, often it's what's the limitation of your device or your technique. That's what that's what the real sources of errors are really about. Other questions? Okay, well, thanks everyone for, some of you popped in late. We were talking about how it's fall break for many people, and I didn't expect a lot of people to show, but we got good numbers. So that's great. Next week, we'll do standard candles, our Lyraes, Cepheids, and type 1As. Also a lab with kind of this repetitive but good reinforcing repetitive structure. All right. I'll see you all later.
Thank you.
Thanks, Dan. Happy fall break.
Thanks.
Thank you, Dan.
Pleasure.